Hello everyone, welcome to Let's Learn. I am Aparna from the Department of Artificial Intelligence and Data Science. In this video, we are going to learn some of the digital lab experiments. The first experiment is the study of logic gates. What is logic gate? Logic gates are used to carry out the logical operations on single or multiple binary inputs and result in one binary output. First, we are going to see AND gate. Dragging the AND gate and placing over here. There are two inputs in AND gate and one output. When the bulb glows, the output is 1. When the bulb does not glow, the output is 0. The expression of AND gate is A dot B. When A and B are 0 and 0, the output is 0. When A is 0 and B is 1, the output is 0. When A is 1, B 0, the output is 0. When A1 and B1, the output is 1. This is the circuit of AND gate. Next, OR gate. Two inputs and one output. Connecting the input and output. The expression of OR gate is A plus B. When A0, B0, the output is 0. When A0 and B1, the output is 1. When A1, B0, the output is 1. When A1 and B1, the output is 1. This is the circuit of OR gate. Next, we are going to see NOT gate. In NOT gate, there is only one input and one output. The output of the NOT gate is the complement of its input. When A is 0, when the input is 0, the output is 1. When the input is 1, the output is 0. This is the circuit of NOT gate. Next, we are going to see XOR gate. In XOR gate, there are two inputs and one output. The expression of XOR gate is A bar B plus A B bar. For easier understanding, when both the inputs are same, the output is 0. When one of the input is different, the output is 1. When A and B are 0, the output is 0. When A is 0, B is 1, the output is 1. It is because one of the input is different from other. When A is 1, B is 0, the output is 1. When A1 and B1, the output is 0. Here, both the inputs are same. This is the circuit of XOR gate. Next, we are going to see NAND gate. Having two inputs and one output. So the expression of NAND gate is A dot B whole complement. The output of NAND gate is the complement of the output of AND gate. So when A and B are 0, the output is 1. When A0, B1, the output is 1. When A1, B0, the output is 1. When A and B are 1, the output is 0. This is the circuit of two input NAND gate. Next, we are going to see three input NAND gate. Placing NAND gate here and increasing the input count of NAND gate. As there are three inputs, we are using three switches and a single output. The expression of the three input NAND gate is y equal to A dot B dot C the whole complement. When A, B and C are 0, the output is 1. When A 0, B 0 and C 1, the output is 1. When A0, B1, C0, the output is 1. When A0, B1, C1, the output is 1. When A1, B0, C0, the output is 1. When A1, B0, C1, the output is 1. When A1, B1, C0, the output is 1. When when the three inputs are 1, the output is 0. This is the circuit of 3 input NAND gate. Next we are going to see NOR gate. In NOR gate there are 2 inputs and a single output. Connecting the inputs and outputs. The expression of NOR gate is A plus B whole bar. The output of NOR gate is the complement of the output of OR gate. When A0, B0, the output is 1. When A0, B1, the output is 0. When A1, B0, output is 0. When A1, B1, the output is 0. This is the circuit of NOR gate. So as a result, the functions of all basic logic gates are studied and verified. The next experiment we are going to see is the study of adders and subtractors. What is half adder? A half adder is a combinational circuit, needs two binary outputs. The input variables designate the AND and addend bits. The output variables produce the sum and carry. The half adder can be implemented with an exclusive OR and an AND gate. Full adder. What is full adder? A full adder is a combinational circuit that forms the arithmetic sum of input. It consists of 3 inputs and 2 outputs. A full adder is useful to add 3 bits at a time. In full adder, some output will be taken from XOR gate, carry output will be taken from OR gate. What is a half subtractor? The half subtractor is constructed using XOR and AND gate. The half subtractor has 2 input and 2 outputs. The outputs are difference and borrow. The difference can be applied using XOR gate. Borrow output can be implemented using an AND gate and an inverter. What is a full subtractor? The full subtractor is a combination of XOR and OR NOT gates. In a full subtractor, the logic circuit should have 3 inputs and 2 outputs. The sum of half subtractor must put together gives a full subtractor. The first half subtractor will be C and AB. The output will be difference output of full subtractor. The expression AB assembles the borrow output of the half subtractor and the second term is the inverted difference output of first XOR. First, we are going to see half adder. For half adder, we need 2 gates, an XOR gate and an AND gate. In half adder, there are 2 inputs and 2 outputs. The output from the XOR gate is the sum and the output from the AND gate is the carry. Connecting the inputs and outputs. So, both the inputs should be also connected to AND gate. So this is the sum and this is the carry. When A and B are 0, the sum and carry are 0 and 0. When A0, B1, the sum is 1 and carry is 0. When A1, B0, sum is 1, carry is 0. When A and B are 1, the sum is 0, carry is 1. This is the circuit of half adder. Next, we are going to see full adder. In full adder, we need 2 XOR gates, 2 AND gates and a OR gate. So, 2 XOR gates, 2 AND gates and a OR gate. So in a full adder there are 3 inputs connecting the first 2 inputs to the first XOR gate. The input of the second XOR gate is one of the input of the second XOR gate is the output of the first XOR gate, and the third input. And for the AND gate, first 2 inputs should be given to the AND gate. For this second AND gate, the output of first XOR gate should be a 1 input, and the third input should be given as another input. The OR gate should be connected with both the AND gates. So there are 2 outputs connecting the output. The output from the XOR gate is the sum, and the output from the OR gate is the carry. When A, B and C are 0, the sum and carry is 0. When A 0, B 0, C 1, the sum is 1 and carry is 0. When A 0, B 1, C 0, sum is 1, carry is 0. When A 0, B 1, C 1, sum is 0, carry is 1. When A 1, B 0, C 0, sum is 1, carry is 0. When A 1, B 0, C 1, sum is 0, carry is 1. When A1, B1 and C0, sum is 0, carry is 1. When A1, B1 and C1, both the sum and carry are 1. This is the circuit of full adder. Next we are going to see half subtractor. For half subtractor we need an XOR gate, an AND gate and a NOT gate. So there are 2 inputs. So connecting the inputs to the XOR gate, and the input of the NAND gate should be connected as follows. So one of the input, that is named as A, should be connected to the NOT gate. The input of the one of the input of AND gate is the input B. Another input of AND gate is the output of NOT gate. Now there are 2 outputs. The output from the XOR gate is the difference, and the output from the AND gate is the borrow. When A 0, B 0, both difference and borrow are 0. When A 0, B 1, both difference and borrow are 1. When A 1, B 0, difference is 1 and borrow is 0. When A1, B1, both difference and borrow are 0. This is the circuit of half subtractor. Next we are going to see a full subtractor. In full subtractor we need 2 XOR gates, 2 AND gate, 2 NOT gates and an OR gate. In a full subtractor there are 3 inputs, input A, input B and input C. So the input A and B are connected to the first XOR gate. The output of first XOR gate is connected to the one of the input of second XOR gate, and the third input C is connected as another input. Now the input A is connected to the NOT gate and the output of NOT gate is connected as one of the input to the first AND gate. And the input B is connected as the another input to the first AND gate. And the output of first XOR gate is connected to the NOT gate. The third input is connected as one of the input to the AND gate and the another input is the output of second NOT gate. The inputs of OR gates are both the outputs of NAND gate, AND gate. So this is the circuit of full subtractor and we need to add outputs to this. The output of first XOR gate is the difference and the output of second XOR gate is the borrow. So when A0, B0 and C0, both the difference and borrow are 0. When A0, B0, C1, both difference and borrow are 1. When A0, B1, C0, both difference and borrow are 1. When A0, B1, C1, the difference is 0 and borrow is 1. When A1, B0, C0, difference is 1, borrow is 0. When A1, B0, C1, both difference and borrow are 0. When A1, B1, C0, both the difference and borrow are 0. When A, B and C are 1, both the difference and borrow are 1. So this is the circuit of full subtractor. The next experiment is the code converter 1. In this code converter, we are going to see binary to gray code converter and gray code to binary code converter. So, binary to gray code conversion is a very simple process. So, let's see the binary to gray code converter. So, first, know about the conversion of binary to gray. So, 1010 is the binary representation of the decimal value 10. So, how to convert this binary value to a gray code? So, here apply the XOR conversion. So the first bit 1 should be returned directly as 1. Next, consider the first two bits 1 and 0. In XOR operation, when both the inputs are same, the output should be 0. When any one of the input is different, the output is 1. So consider that here. So consider first two bits 1 and 0, both are different. Then we should write it as 1. Next consider the second and third bit 0 and 1. They both are different. So again we have to write it as 1. Next consider the third and fourth bit 1 and 0. Here both the bits are different. So return it as 1. So the binary to gray code conversion has been done here. The gray code equivalent of the binary code 1010 is 1111. So this is how the conversion should be done. So to understand this more better, let's see the circuit diagram of binary to gray code converter. So for this we need 3 XOR gates. As we are applying 3 XOR conversions here and 4 inputs and 4 outputs. So the first bit should be returned directly. So the first input is the direct output. So the second and third bit, first and second bit are undergoing the first XOR conversion. So connect the first two inputs to the first XOR gate, and the second two bits, that is the second and third bit, are undergoing the second XOR conversion. So connect the second and third bit to the second XOR gate. Similarly, the third and fourth bit input to the third XOR gate. Connect these to the outputs. So let's see one example. As I already said, the binary code 1010 has the gray code equivalent 1111. Let's verify it. First bit 1, second bit 0, third bit 1, fourth bit 0. The output is 1111. So this is the binary code 1010 has 1111 as the gray code equivalent. It is verified. So let's see another example. So 1011. So this is 11, decimal equivalent 11. So let's verify the gray code for it. First in bit 1, second bit 0, third and fourth bit are 1. So the gray code is 1110. So it is verified. So this is the circuit of binary to gray code converter. Next we are going to see gray to binary code converter. So 0011 is the gray code. Let's see how to convert this gray code to a binary code. So write the first bit as it is. Next, the output of the first bit should be XOR operated with the second bit of the gray code. So 0 and 0, both the bits are same. So again it should be 0. Now the second output should be XOR operated with the third bit of gray code 0 and 1. So both the bits are different, so 1. Now the third output should be XOR operated with the fourth bit of gray code 1 and 1. So both are same, so 0. So this is the binary code equivalent for the gray code 0011. Let's understand it with the circuit diagram. So for the circuit diagram of gray to binary code converter, we need four XOR gate, 4 inputs, four outputs, so connecting the first bit as it is directly to the output. Sorry, we need only three XOR gates. So the second bit to the second XOR gate, and the another input should be given from the output. So since the output is directly the first bit, we should connect the first input directly. Next, the third input and the output from the second input should be XOR operated. Now the fourth bit and the input from the third and second bit should be connected to the third XOR gate. It should be connected to the output. So let's verify this gray code to binary code converter. So first first bit 0, second bit, let's take this from down. First bit 0, second bit 0, third bit 1, fourth bit 1. So the output also should be taken from down. 0 0 1 0. So it is verified. So let's check on another input and another output. So let's check on 0 triple 1, 0 triple 1. The output should be 0 1 0 1. So this is the circuit of gray code to binary code converter. The next experiment is the code converter 2. To implement a 4-bit BCD to XS3 code converter, XS3 to BCD code converter. So a BCD is an abbreviation for binary coded decimal. BCD is a numeric code in which each digit of a decimal number is represented by a separate group of bits 8421. So a XS3 code is a modified form of a BCD number. The XS3 can be derived from the natural BCD code by adding 3 to each coded number. That is the XS3 code. Let's see the circuit diagram of BCD to XS3 converter. So before that, we have to see the conversion from BCD to XS3. 0010 is a BCD form of decimal value 2. To convert this into XS3, we need to add 3 to it, that is 0011, binary form of 3 to it. It gives the XS3 code of 2 as 0101. So let's verify this with this circuit diagram. So 0010, first bit 0, second bit 0, third bit 1, fourth bit 0, the output is 0101. So thus the circuit diagram of BCD to XS3 code has been verified. Next we are going to see XS3 to BCD converter. This is a circuit diagram of XS3 to BCD converter. This is the reverse process of the BCD to XS3 converter. In BCD to XS3 converter, we add 3 to a BCD value to change it as a XS3 code. In this process, and a 3 should be minus from the XS3 code to get the BCD value. So in that case, let's check on the XS3 code 0111, 0111, 0111. In this case, when 3 is minus from 7, we should get 4, 0100. So this is the circuit diagram of XS3 to BCD converter, and it is verified. The next topic we are going to see is the parity generator. Parity is used for purpose of detecting errors and transmission of binary information. A parity bit is an extra bit included with a binary message to make the number of ones either odd or even. The message including the parity bit is transmitted and then checked out the receiving end for errors. So the digital information is in a binary form. If it is transmitted from one digital system to another system, an error may occur due to transients, noise, and other disturbances. The circuit used for generating parity bit is called parity generator. How to determine the odd and even parity? So, if there is no ones in a binary code, then it comes under odd parity. If there is 1 1, then it comes under even parity. If there is 2 1, then it comes under odd parity, and if 3 ones, it come under even parity. So this is the circuit diagram of parity generator. So for first evaluating for 0 0 0, that is no ones here, so it comes under odd parity. 0 0 1, that is 1 1 here, it comes under even parity. 0 double 1, there are two ones here, it comes under odd parity. Triple 1, it comes under even parity, as there are three ones here. So this is the circuit diagram of parity generator. The next experiment we are going to see is the multiplexer and demultiplexer. What is multiplexer? Multiplexer means transmitting a large number of information units over a small number of channels or lines. A digital multiplexer is a combinational circuit that selects binary information from one of many input lines and directs it to a single output line. The selection of a particular input line is controlled by a set of selection lines. Normally, there are two n input line and n selection lines whose bit combination determine which input is selected. What is demultiplexer? The function of demultiplexer is in contrast to multiplexer function. It takes information from one line and distributes it to a given number of output lines. For this reason, the demultiplexer is also known as a data distributor. Decoder can also be used as demultiplexer. In the 1 to 4 demultiplexer circuit, the data input line goes to all of the AND gates. The data select lines enable only one gate at a time, and the data on the data input line will pass through the selected gate to the associated data output line. First, see the circuit diagram of multiplexer. In a multiplexer, there are two selection inputs. These are the two selection inputs and these are the data inputs. This represents 0, 1, 2 and 3. So 0th bit, 1th bit, 2nd bit and 3rd bit. Selection line indicates which type of bit should be given to the multiplexer. When the selection lines are 0 and 0, 0th bit should be 1. Then the single output should also be 1. If the selection lines or inputs are 0, 1, 0, 1 indicates 1. So 1 should be given. Here the output is 1. If the selection lines are 1 and 0, 1 0 represents 2, then the second bit should be given. Here the output is 1. If both the selection inputs are 1 and 1, it represents 3, so the third bit should be turned on and it gives the output as 1. So this is the circuit diagram of multiplexer. Let's see the demultiplexer, which is an exact opposite from the multiplexer. In multiplexer, there are two selection inputs, four data inputs and a single output, but in demultiplexer, the two selection inputs are the same, but there are only one data input and four outputs. So when the selection lines are 0 and 0 and when the input data is also 0, there is no change in the output. When the selection lines are as it as 0 and 0, when the input data is 1, it shows 1 triple 0, which represents 1. If the selection lines are 0, 1 and the input data is 0, there is no change. It's all the outputs are 0. If the selection lines are 0 and 1 and the input data is 1, 0, 1, 00, it represents 2 as per the selection line 0, 1 represents 2. When the selection lines is 1 and 0 and the input data is 0, the output is 0. When the selection line is 1, 0 and the input is 1, it is 0, 0, 1, 0 which represents 3, which represents 2 as per the selection line. When the selection lines are 1, 1 and the input data is 0, the output is 0. With the same selection inputs, when the input is 1, it represents 3. So this is the demultiplexer. The next experiment is the encoder and decoder. The encoder is a digital circuit that performs inverse operation of a decoder. An encoder has two n input lines and n output lines. A decoder is a multiple input, multiple output logic circuit which converts coded input into coded output where input and output codes are different. So let's see the circuit diagram of encoder first. It has 7 input datas and 3 output datas y1, y2, y3, y4, y5, y6, y7. When y1 is 1, it represents 0, 0, 1. When y1 is 1, it represents 1, 0, 0, 1. When y2 is 1, it represents 0, 1, 0, 2. When y3 is 1, it represents 0, 1, 1, 3. When y4 is 1, it represents 1, 0, 0, 4. When y5 is 1, it represents 1, 0, 1, 5. When y6 is 1, it represents 1, 1, 0, 6. When y7 is 1, it represents 1, 1, 1, 7. So this is the circuit diagram of an encoder. Let's see the decoder. Decoder is the reverse process of encoder. So when both the inputs are 0 and 0, it represents 0. So 1, 0, 0, 0. This is D0, D1, D2, D3. When both the inputs are 0, 0, D0 glows up. 0, 1. D1 shows 1. When 1, 0, D2 shows 1. When 1, 1, D3 shows 1 which represents 3. So this is the circuit diagram of decoder. The next experiment we are going to see is the study of flip-flops. We are going to see RS flip-flop, D flip-flop, JK flip-flop. What is RS flip-flop? The clocked RS flip-flop consists of NAND gates and the output changes its state with respect to the input on application of clock pulse. What is D flip-flop? To eliminate the undesirable condition of indeterminate state in the SR flip-flop, when both inputs are high at the same time, in the D flip-flop, the inputs are never made equal at the same time. This is obtained by making the two inputs complement of each other. What is JK flip-flop? The indeterminate state in the SR flip-flop is defined in the JK flip-flop. JK inputs behave like S and R inputs to set, reset and flip-flop. The output Q is AND with K input and the clock pulse. Similarly, the output Q dash is ANDed with J input and the clock pulse. So first we can see the SR flip-flop in which there are two inputs S and R and a clock pulse, and the second pair of NAND gates have one input as an output of another, and it represents present state, it represents the next state. So when S and R are 0 and 0, present state and the next state shows the memory state. When S is 0 and R is 1, it represents 0, 1. When S is 1 and R is 0, it gives 1 and 0. When both are 1, it represents 1 and 1, which is not used due to the clock pulse. Next, we are going to see the D flip-flop. In the D flip-flop, we need 4 NAND gates as the same in the SR flip-flop. In D flip-flop, there are 2 inputs, but the second input should be the complement of the first input. So giving the first input, for the second input, we are just using a NOT gate. The second input is the complement of the first input. Next, giving clock pulse. Connecting these inputs. So in D flip-flop, when the input is 0, the next state is the present state is 0 and the next state is 1. When input is 1, the present state is 1 and the next state is 0. So this is the circuit diagram of D flip-flop. Next we are going to see JK flip-flop. For this also we need 4 NAND gates. There are 2 inputs J and K. J is set and K is reset input. And we have clock. We need 3 input NAND gate. So giving these inputs. Giving clock pulse input. Connecting these gates. There are 2 outputs. The present state output is the input to the second NAND gate. So this is the circuit diagram of JK flip-flop.